good day everyone. This is Medrano, and I will be presenting our advanced calculus problem with proofs and solutions. So I actually do have a partner, which is Ethel May Ompad. However, I will not be presenting hers because she will also be presenting her set of problems with proofs and solutions on her own video. So I'm just going to run through her problems and we'll go through mine. So our outline is introduction, basic concepts, discussion, and references. So first, introduction. I'm not going to expound this because the discussion is what our main goal is really. So understanding important mathematical ideas like metric spaces, limits, and derivatives, which are the foundation of analysis, requires a solid understanding of advanced calculus. Beyond basic Euclidean spaces, it offers the platform for investigating continuity, convergence, and differentiability in diverse contexts. By ensuring that these structures are logically coherent, the study of axioms enables clearly defined procedures and trustworthy outcomes. Deeper investigation of functions and sequences in complicated contexts is made possible by advanced calculus, which extends the concept of Euclidean spaces to more general metric spaces. Beyond the realm of pure mathematics, advanced calculus is essential for practical applications in disciplines like economic, engineering, and physics. Numerical modeling, optimization, and differential equation solution all depend on the concepts of sequences, limits, and derivatives. Higher dimensional geometry is supported by the study of points and their properties in Euclidean spaces, while axiomatic systems provide the rules required to demonstrate consistency. All things considered, advanced calculus offers the means to model and evaluate dynamic systems in both theoretical and practical settings. So our basic concept, actually the basic concepts and definitions in this paper or in this PPT were drawn from Principles of Mathematical Analysis by Walter Rudin, Understanding Analysis by Stephen Abbott, and Topology by James Moncrief. So I will just go ahead on the definitions and basic definitions and concepts, because our main goal really is the discussion. So the problems and the proofs. So this is our basic concepts: completeness axiom, bounded upper bound, supremum, sequence, limit of sequence, monotonicity of a sequence, monotonic sequence theorem, metric space, closed ball, Cauchy sequence, complete metric space, intersection of nested balls in a complete space, compactness in a metric space, totally bounded metric space, Heine-Borel theorem, open cover, subcover, exponential function limit, limit of a function between metric spaces, sequential criterion for limits in metric spaces, convergence of sequences in metric spaces, and last but not least, mean value theorem. So, in our basic concepts, we got it from 3 different books. But in our discussion or our problems, so we're drawn from only 2 books, which is from the Principles of Mathematical Analysis by Walter Rodin and Understanding Analysis by Stephen Abbott. So these sources present fundamental topics serving as a theoretical foundation for the solutions provided. So this problem number 1, 2, and 3 are actually going to be discussed or presented by my partner, Ethel May Ompad. So I'm just going to go ahead with my problems. So problem 1, 2, 3 is my partner's, while 4, 5, 6 is mine. So we'll just go ahead with it. So 4, problem number 4. The proof of the existence of E via the supremum axiom. So define the set A is 1 plus 1 over n to the power of n, as n is an element of a natural number. So letter A is bounded above in R, thus B is the supremum sub A exists, and C, E is equal to supremum. So, proof and solution. So, let A be a subset of R. Let A sub n be equal to 1 plus 1 over n to the power of n, for each n is an element of natural number. So now observe that as n approaches to infinity, the sequence A sub n behaves similarly to the well-known limit definition of E. which is limit of 1 plus 1 over n to the power of n as n approaches to infinity is equal to e. This actually means that as an approaches e, as n increases, which provides the intuition that the sequence is bounded above by e. So it is bounded above by e simply because as n increases, the sequence is approaching to e. And so A is bounded above in R. So we first show that A sub n is indeed bounded above. We begin by establishing that A sub n is bounded above. We know that 1 plus 1 over n to the power of n is less than or equal to E for all n is an element of natural numbers, since earlier we stated that E is the it bounds it is 1 plus 1 over n to the power of n is bounded above by E as an increases and n increases. So this inequality follows from the fact that the limit of 1 plus 1 over n to the power of n as n approaches to infinity is E. And the sequence 1 plus 1 over n to the power of n is increasing for large n. So therefore, for any n, we have A sub n is less than or equal to E. So whatever happens, however big or how much big n is, it is always be less than E. So this shows that the sequence A sub n is bounded above by E. Consequently, we can conclude that the set A, which is equal to A sub n, as n is an element of natural numbers, is bounded by E. Thus, we have supremum of A is less than E. So, since, as we all know, supremum or upper bound, the definition is its supremum is less than the upper bound. So, since the upper bound of A sub n is actually E, so supremum of A is actually less than E. So B, the supremum sub A exists. So since the set A is bounded above and the sequence A sub n approaches to E, then it follows the supremum axiom. So this axiom guarantees the existence of the least upper bound or supremum of a bounded set. By the completeness axiom, since there exists an upper bound, there also exists a supremum. Therefore, the supremum of A exists and is some value sub A. So, in supremum axiom or completeness axiom, if there exists, as what I said earlier, if there exists an upper bound, there also exists a supremum. Similar to this, right? E is the upper bound. So, we expect that supremum A or the supremum of A, since A is the sequence, since E is the upper bound of A, it means that there exists a supremum of A, which is actually sub A. So the supremum sub A exists in here. So C is we're going to prove that A is actually the supremum also of A, not just the upper bound, but the supremum as well. So to prove that supremum A is equal to E, where A is equal to A sub n, as n is, A is defined as A sub n, as n is an element of natural numbers, and A sub n is equal to 1 plus 1 over n to the power of n. We will apply the theorem 10. So what is theorem 10? It's actually, this theorem was actually, I don't know if I was able to put the basic definition, but I actually I actually get it from our discussion in the past. So the theorem 10 states that let S be a non-empty subset of R and U be an upper bound of S, then U is equal to sup S if and only if for all epsilon is greater than 0, there exists some S is an element of big S such that U minus epsilon is less than small s. Since we know from that behavior of the sequence A sub n that limit of A sub n as n approaches to infinity is equal to E, and the sequence A sub n is equal to 1 plus 1 over n to the power of n is increasing for sufficiently large n, we have A sub n is less than E for all n is an element of natural numbers. This means that E is an upper bound for the set A as defined as A sub n, as n is an element of n. Now, for any epsilon is greater than 0, we know that as n approaches to infinity, the sequence get arbitrarily close to E. This implies that for any epsilon greater than 0, there exists some n, big N, that is an element of natural numbers, such that for all small n is greater than or equal to bigger n. We have E minus the epsilon is less than A sub n, which is also less than E. So thus for every epsilon is greater than 0, there exists some A sub n is an element of A, such that E minus epsilon is less than A sub n, which is also less than or equal to E, satisfying the condition for theorem 10. Now, by theorem 10, since E is an upper bound of A, and for every E epsilon is greater than 0, we can find an element A sub n, which is an element of A, such that E minus epsilon is less than an, and an also is less than or equal to E. We conclude that supremum A is equal to E. Therefore, we have proven that the supremum of the set A is E. So, number 5, limit of a function between metric spaces. So, let x be x and y dy be metric spaces. Let f be defined as x except the point x sub 0 converges to y be a function. Prove that the limit fx as x approaches to x sub 0 is equal to y sub 0 exists if and only for every sequence xn is a subset of x minus the point x sub 0 such that x sub n approaches to x sub 0. We have function of xn approaches to y sub 0 and y. So let x and dx and y be metric spaces, and let f be defined as x minus x sub 0 as it approaches to y be a function. To prove that limit function of x as x approaches to x sub 0 is equal to y sub 0 exists if and only if every sequence x sub n is a subset of x minus x sub 0 such that x sub n approaches to x sub 0. We have function of xn approaches to y sub 0 in y verges. So first is let fx and x limit of fx as x approaches to x sub 0 is equal to y sub 0. Suppose that x sub n is a subset of x minus the point x sub 0 be a sequence such that x sub n approaches to x sub 0. By the definition of the limit for every epsilon is greater than 0, there exists a delta such that if is that a delta? Or was it I don't know how to read that, but I believe it's delta. Wait, let me check. Yes, it's delta. Delta, then such that if d sub x sub 0 is less than delta, then d sub y, function of x and y sub 0 is less than epsilon. Since as x sub n approaches to x sub 0, there exists a bigger n such that for all smaller n is greater than or equal to n or bigger n, we have dx xn x0 is less than delta. Therefore, for all n, which is small, is greater or equal to bigger n. So dy f function of xn y0 is less than epsilon. Thus, the function of xn as approaches to y sub 0 in y. So suppose for every sequence x sub n is subset of x minus x sub 0 such that x sub n approaches to x sub 0, we have f function of x sub n as it approaches to y sub 0 in y to show that the limit of function of x as x approaches to x sub 0 is equal to y0. Suppose by contradiction that the limit does not exist, then there exists some e sub 0 is greater than 0 such that for every delta is greater than 0, there exists a small x is an element of x minus x sub 0 such that dx x sub 0 is less than delta and dy function of x y sub 0 is greater or equal than e sub 0. Constructing a sequence x sub n is a subset of x minus x sub 0 such that dx x sub n x sub 0 is less than 1 over n, but dy, a function of xn, y sub 0 is greater or equal to epsilon 0. Then x sub n approaches to x sub 0, but by assumption, we also have f function of x sub n does not approach to 1 sub 0, which contradicts the sequential criterion for limits in metric spaces. So, the sequential criterion for limits in metric spaces states that a function defined as x approaches to y has limit y sub 0 at x sub 0. 0 is an element of x if and only for every sequence x sub n approaches to x sub 0, function of x n approaches to y sub 0. Thus, the limit of fx, which x approaches to x sub 0 is equal to y sub 0. Therefore, the limit of fx as x approaches to x sub 0 is equal to y sub 0 exists if and only for every sequence x sub n is an element of x minus x sub 0 such that x sub n approaches to x sub 0, we have function of x sub n as approaches to y sub 0 in y. So yes. So that one I find it actually very hard, but this one is very much easy. So the problem is let the function of x is equal to ln x on the interval 1 and e, close interval 1 and e. Use the mean value theorem to show that there exists some c is an element of 1 e such that the first derivative of c is equal to the function of e minus function of 1 all over e minus 1. So the preferred solution, the function of x is equal to ln x is continuous on the closed interval 1 and e and differentiable on this open interval 1, e satisfying the hypothesis of the mean value theorem. So this is actually the condition for a mean value theorem. So the average rate of change of f over 1 and e is f function of e minus function of 1 e minus 1 is equal to ln e minus ln 1 over e minus 1, which is actually 1 minus 0 and e minus 1. So 1 over e minus 1. So since the derivative of f of x is a 1 over x, the mean value theorem guarantees a point c is an element of 1e such that the function of c or the first derivative of the function c is equal to also 1 over c, which is actually 1 over e minus 1. Solving for c gives, since the numerator is the same, just going to be the denominator. So c is equal to e minus 1. So, which lies with the interval 1e because 1 is less than e minus 1, which is also less than e. So, noting that e is approximately 2.718. Hence, the value of c is equal to e minus 1 satisfies the conclusion of the mean value theorem. So, yes, since, as you can see, e minus 1 actually lies inside the 1 and e. So, it follows that c is really e minus 1. So that concludes our or my presentation. And this is our references. And with that, my partner will actually be also presenting her problems, which is 1, 2, and 3, and she will be the one discussing. And that's all for today. Thank you.